In this video, I'm going to be reviewing the Recitation Week 7 packet for Dr. Collini's Chem 2380 class. The first part of this packet asks us to take a look at the mechanism for an electrophilic aromatic substitution, and then try recreating it using the electrophiles given. Electrophilic aromatic substitution is a reaction that allows substituents to be added to an aromatic ring. So the first step always includes one of the double bonds from the ring reaching out and attacking an electrophile, which generates a resonance stabilized carbocation within the ring. And then in step 2, a base comes and deprotonates part of the ring, which is able to regenerate aromaticity. Now let's try recreating that mechanism using Cl+ as the electrophile. So step 1 is going to be one of the double bonds reaches out and attacks the chlorine, which will generate a positive charge on one side of the double bond and a bond to chlorine on the other. And the reason it's positively charged is because the carbon with the positive used to have 4 bonds, and when the electrons moved to attack the chlorine, it was left with only 3 bonds. The positive charge is directly adjacent to another double bond within the ring, which means that it is capable of resonating. So I'm going to draw that resonance structure now. As you can see, I've drawn arrows representing the double bond on the middle moving up to the top, and the positive charge is then able to move down to the bottom left, and then again it's adjacent to the bottom double bond, so we can generate a third resonance structure as shown here. In step 2, a base is added to the reaction, which is capable of deprotonating at the position where the electrophile was attacked. So I'm going to draw in the proton here that is about to be deprotonated, and I've drawn just a generic B for any base. It's going to reach out and steal the proton, and then the electrons that were being shared to make that bond are going to collapse down to where the cation is, which will regenerate our aromatic molecule. Let's try another example, this time using the nitronium ion as the electrophile. So again, I'm just going to draw benzene and NO2+. Just like before, the first step in this mechanism is for one of the double bonds in the benzene ring to reach out and attack at the electrophilic position, which in this case is the nitrogen atom. And when this happens, one of the double bonds to the oxygen will be pushed back up onto the oxygen so that the nitrogen does not have 10 bonds, or 10 electrons. Since benzene doesn't have any substituents, it doesn't matter which double bond we use, and it also doesn't matter which side of the double bond the electrophile attaches to. So in this case, I've decided to put the electrophile on the right side of the double bond and the carbocation on the left side of the double bond. So this is just one of the 3 resonance structures, but I'm going to go ahead and draw all 3 of them again so you can see what the resonance structures look like, and you can see where the positive charge is going to reside in this intermediate. Notice that the carbocation is going to be present on every other carbon within this ring. This isn't super important right now, but when we start talking about directing effects next week, we will learn that it's important to pay attention to areas of electron density within the ring, because not every carbon is going to be equally reactive now that we have a substituent coming off of the ring. So this is just kind of helping you to get ready for what's coming in the next week. Moving on to step 2, I'm again just going to use a generic base, and it's going to reach out and attack at the position where the nitro group is present. So I'm going to draw in the hydrogen that's attached to that carbon. It's going to be deprotonated, and the electrons within that bond are going to collapse down where the carbocation is, which will regenerate our aromatic molecule. In the intermediate, I didn't draw out the NO2 with all of its bonds, but I think it's important to recognize what that structure looks like, so I'm going to draw them here. Notice that the nitrogen has a +1 formal charge, and one of the oxygens has a -1 formal charge, but overall this is a net neutral compound. If this mechanism seems complicated to you, I think it's helpful to relate it back to the E1 mechanism that we learned in Organic Chemistry 1. So I'm going to draw that here. Remember, the first step for an E1 mechanism is the leaving group leaves, and we generate a carbocation. And then once we have a carbocation, we're able to use a base to deprotonate one of the protons on an adjacent carbon, and then the electrons from that proton will then collapse down to where the carbocation is, creating a double bond. This is the exact same thing that we see in the electrophilic aromatic substitution. We have a base that grabs onto one of the protons that's adjacent to the carbocation, and then the electrons from the proton collapse down to create that double bond. So if you can see the similarities between those two mechanisms, it might help you when you are asked to draw mechanisms for the E1 reaction later on a potential homework quiz. In question 2, we're asked to take a look at the following molecules, and particularly the lone pairs within each of these molecules, and determine if the lone pairs would prefer to be in a hybridized orbital or in a conjugated pi orbital. I think it's helpful to remember our rules for aromaticity when we do this exercise, so I'm going to go ahead and write those down now. So in order for a compound to be aromatic, it needs to have 4n plus 2 pi electrons. It also needs to be planar, and it needs to have a complete ring of pi orbitals that are all connected. The rules for anti-aromaticity are almost the exact same, but instead of 4n plus 2 pi electrons, it's just 4n pi electrons. So looking at this first molecule, we have a 7-membered ring that has 6 electrons in the existing double bonds, with the potential for that remaining lone pair to also enter into the conjugated highway if it occupies a pi orbital. However, if it were to do that, we would have 2, 4, 6, 8 total pi electrons, which follows the rules for anti-aromaticity. Since 8 is a multiple of 4n, the lone pair on this ring is going to prefer to remain in a hybridized sp3 orbital to avoid anti-aromaticity. And the way that we know it's an sp3 hybrid orbital is we're going to take a look at the electron domains on that carbon. We have 2 bonds that are drawn and 1 lone pair, and then we can assume because the formal charge is -1, there's going to be an implied hydrogen. So that makes 4 total electron domains, which is sp3. In the next example, we have a 5-membered ring with 2 double bonds and potentially a lone pair that's able to resonate into the ring. We know that we can't have 2 lone pairs from the same atom resonating into the ring and contributing to resonance, but there's potential for at least one of them. And if that were the case, we would have 6 total electrons in the aromatic system, or in the ring system. To check the rules for aromaticity, I'm going to set 4n plus 2 equal to 6, and then solve for n. If n is equal to a whole number integer, then the rules for aromaticity have been met. If we solved for n and it was a fraction or decimal, this would not meet the rules for aromaticity, and this molecule would not be aromatic. Since n was a whole number, we can reasonably assume that one of the lone pairs on the oxygen is going to be in a conjugated pi orbital, and the other one is going to remain in a hybrid sp2 orbital. With one of the lone pairs being in a conjugated pi orbital, we now have a pi orbital on every atom within the ring, so we have a complete ring of pi orbitals, and that conjugated lone pair is capable of resonating down, creating a double bond, which then means that the oxygen has 3 electron domains, 1 to the left, 1 to the right, and 1 with the remaining lone pair, which means that the remaining lone pair is sp2 hybridized. In this next example, we have an 8-membered ring that has 3 double bonds and 2 lone pairs, but we know that only one of those lone pairs can potentially participate in resonance, which means that we have 8 possible pi electrons. Now we could do the same math as before and set 8 equal to 4n plus 2 to see if this meets the rules for aromaticity. However, this ring does not have a complete set of pi orbitals, because if we were to draw in all of our pi orbitals, we would have one on either side of the double bonds, but there's not one on that final remaining sp3 hybridized carbon. So this does not meet the rules for aromaticity or anti-aromaticity. So if I were to draw in those 2 hydrogens, you can see that this is an sp3 hybridized carbon, so we don't actually need to worry about the rules for aromaticity or anti-aromaticity, because this does not have a complete ring of pi electrons. So now we just have to remember our basic rules for resonance structures to determine if the lone pair prefers to remain isolated in a hybrid orbital, or if it would prefer to be in a conjugated pi orbital so that it's capable of resonating with its attached double bonds. So in this case, if it is able to resonate in, we would have overall greater resonance within the molecule, which tends to lead to increased stability. So one of those lone pairs is going to form a double bond, creating a lone pair on the top left carbon. So I'll go ahead and draw this resonance structure now so you can see what I'm talking about. So if the lone pair were to form a double bond, we'd have a lone pair 2 carbons over. And then from there, that lone pair could resonate again, creating a new lone pair on the top right carbon and a double bond between the left and the top left carbons. And then we could show this one more time with, oh sorry, the lone pair on the sulfur should have also been erased when the double bond was formed. And then we could have one more resonance structure where the lone pair creates a double bond on the right side and the right double bond becomes a lone pair on the bottom right. This is the furthest that the lone pair is capable of resonating. If we tried to draw another resonance structure with the lone pair moving, again, clockwise, it would create a fifth bond with that sp3 hybridized carbon, which we know is not allowed. So it cannot resonate further, which means that we now have lone pairs, on just the following carbons, as you can see here. So with all of that said, we do not have a complete ring of pi orbitals, so this is not aromatic, but one of the lone pairs is capable of resonating, which means that one lone pair on the sulfur is going to be in a hybrid sp2 orbital, and the remaining lone pair is in a conjugated pi orbital that's capable of resonating. So let's go ahead and draw that now. I'm going to erase the 8 possible pi electrons, since that doesn't matter, since we know that it is not an aromatic or anti-aromatic molecule. I'm going to label this bottom one as sp2 and the left one as pi, but it could have been alternated the other way. It doesn't matter which one is which, as long as one is pi and one is hybrid. In the next example, we have another 7-membered ring, this time with pi orbitals on either side of the double bond and potentially a pi orbital on the oxygen if this is an aromatic ring. So we do have a potential for a complete ring of pi orbitals. Each double bond has 2 pi electrons, so we would have 2, 4, 6, plus one of the lone pairs, which would be 8 total possible pi electrons, assuming we have a complete ring. 8 follows the anti-rule of 4n, so both of the lone pairs on the oxygen are going to prefer to remain in hybrid orbitals for the sake of avoiding anti-aromaticity, which we know is a high energy state. So both of these are going to be sp3 because that oxygen now has 4 electron domains. Those electrons are all going to be localized, so we no longer have a complete ring of pi electrons, and the molecule is considered non-aromatic. The next molecule is a 5-membered ring that has pi orbitals on either side of the double bond and possibly has a pi orbital on the nitrogen if it's favorable. So let's check and see if it meets the rules for aromaticity. So we have 2, 4, 6 possible pi electrons, which, as we calculated before, does meet the rules for aromaticity, so it means that lone pair is going to be in a conjugated pi orbital. The pi electrons are then capable of resonating down into the ring, as you can see here, creating a double bond between the nitrogen and the carbon and putting a lone pair on that bottom carbon, which is then able to further resonate, creating a complete delocalized ring of pi electrons. So let's go ahead and write that in. This lone pair is in a pi orbital. The next example is one that Dr. Collini discussed in class after your quiz on Friday. We pulled up the article that was published in 2013, where researchers found that this molecule is in fact non-aromatic. But let's go ahead and prove it here. So I'm going to draw in the pi orbitals on either side of the double bond, and there's a potential that that lone pair also is in a pi orbital, but that would mean that we have 4 total electrons, pi electrons, which meets the rules for anti-aromaticity, which we know is unstable. I still think it's helpful to go through the math on this, so I'm going to set 4 electrons equal to 4n and solve for n. In this case, n is a whole number integer, which means that this meets the rules for anti-aromaticity. We could also set 4 equal to 4n plus 2 to see if it meets the rules for aromaticity and just prove to ourselves that it doesn't. So again, 4 is equal to 4n plus 2, solve for n. N is going to be equal to 2 over 4 or 1/2, which is not a whole number, so this molecule cannot be aromatic. Since we know that anti-aromatics are unstable, the lone pair is going to prefer to remain in a hybridized sp3 orbital in order to avoid anti-aromaticity. So let's go ahead and draw that in now. Again, we know it's going to be sp3 hybridized because if we were to draw in the invisible hydrogen, the carbon has 4 electron domains, which is sp3. In this next example, we have a 5-membered ring that has 2 double bonds and 1 lone pair, so 6 total possible pi electrons, which, as we calculated previously, 6 pi electrons does meet our 4n plus 2 rule, so far it's looking like this might be aromatic, but let's double check that it has a complete ring of pi electrons. So if I were to draw the pi orbitals on either side of the double bond, plus the pi orbital for the lone pair, this is a complete ring of pi electrons, which means that our rules for aromaticity are met, and this lone pair is going to prefer to reside in a pi orbital. The next example is a 6-membered ring that has alternating double bonds similar to a benzene ring. However, one of the carbons is replaced by a nitrogen that has a lone pair. If we draw in all of the pi orbitals on either side of the double bonds, we can see that this is a complete ring of pi orbitals, so far that checks off our box for both aromaticity and anti-aromaticity. This lone pair is not going to participate in resonance because we already have a double bond on the nitrogen, and we can't have both of them participating in resonance. So the lone pair must remain in a hybrid orbital, and we know it's going to be sp2 hybridized because the nitrogen has 3 electron domains, which is sp2. In the last example, we have a 5-membered ring that already has 2 double bonds within the ring, so I'm going to draw the pi orbitals on either side of those double bonds, and then the oxygen atom is the only atom in the ring that doesn't have a pi orbital yet. But if one of the lone pairs were to go into that pi orbital, we would have 2, 4, 6 total pi electrons, which meets our rules for aromaticity. So that means that one of those lone pairs is going to be favored to be in a pi orbital, and we can't have both sets of lone pairs in a pi orbital, so one is going to be a pi orbital and one is going to be a hybridized orbital. And we know it will be sp2 hybridized because the pi electrons will be forming a double bond into the ring, so there's a total of 3 electron domains around the oxygen. And similarly, the lone pair on the nitrogen is also going to be sp2 hybridized because the nitrogen already has a double bond into the ring. In question 3, we are asked to name a bunch of molecules, so let's take a look at that very first one. That's just a structure that you are expected to know and memorize. It's a benzene ring with a methyl group. This is known as toluene. The next structure has a methyl group and a OCH3 group. We've learned parent chains for both of these, but we need to determine which one has higher priority and gets to be the parent and which one is going to be treated as a substituent. For this, we're just going to refer back to our naming rules from OChem 1. There is a document in Canvas that shows priorities, but for the sake of this, I'm just going to tell you that the oxygen is going to have the higher priority, so I'm going to label that as carbon 1. And then I'm going to number around the ring so that the methyl group has the lowest possible number. So in this case, I'm going to number clockwise so that the methyl group is on carbon 3. If I'd numbered counterclockwise, the methyl group would be on carbon 5, which is higher than 3, so we're going to stick with the clockwise direction. So now to put this all together in a name, the parent name for the group with an OCH3 coming off of benzene is known as anisole. So the parent is anisole, and then we have a methyl on carbon 3. So the next molecule has a bromine and an amine. Since amine is higher priority, we're going to give that the distinction of carbon 1, and then we're going to number counterclockwise so that bromine is carbon 2 instead of being carbon 6. Actually, let's go back to the previous example. I just realized that I didn't use the orthometa-para designation, so instead of naming it 3-methylanisole, we could have named it M-methylanisole because the two groups are meta to each other. Both naming conventions are considered correct, and you're able to use either one to name this compound. Going back to the previous example with the bromine and the amine, the parent name for this compound is aniline, and there's a bromine on carbon 2, so this is 2-bromoaniline, or we could call it O-bromoaniline because the two substituents are ortho to one another. In the next example, we have 3 substituents, so we cannot use the orthometa-para naming convention because that only works when there are 2 substituents. So in this case, we just have to use the numbering convention as we learned before. The substituent with the highest priority on this molecule is the ketone, so I'm going to label that as carbon 1. To decide whether we number clockwise or counterclockwise, we look to see which direction gives us the lowest numbers on each of our remaining substituents, but as you can see, in both directions, the first substituent is 2 carbons away, so each direction is equally likely. So from here, we just have to decide if the bromine or the methyl is higher priority, and in this case, bromine is higher priority, so I'm going to number through the bromine first and then to the methyl. Now that we have our substituents numbered, we're going to put this all together in a name. So the parent chain is called acetophenone, and we have a bromine on 3 and a methyl on 5. Since bromine comes higher up in the alphabet, we're going to do 3-bromo, 5-methyl acetophenone. The next molecule is a benzene with a fluorine and a methyl group. We don't know any parent names for halides, but we do know a parent name for a methyl group. As we saw in the first example, this is known as toluene. So the parent name for this compound is toluene. So if we number the carbon with the methyl group as carbon 1, we have fluorine on a carbon 3, so the name for this is 3-fluorotoluene. Alternatively, we could name this meta-fluorotoluene or M-fluorotoluene. Since there are two substituents coming off of this benzene ring, both of these naming conventions are correct. The next structure is not a benzene ring, so we're going to name it like we would any other cyclic structure. So look for the highest priority groups. In this case, the double bonds are actually highest priority, so you want to name in such a way that they have the lowest possible number. You could name starting with the left or the right bond, it doesn't matter, they're both equivalent. If you numbered counterclockwise, it would look like this. And if you numbered clockwise, it would look like this. I'm going to number counterclockwise, starting with carbon 1 being on the double bond. Sorry, I messed that up. So double bond has carbon 1 and the ethyl group is carbon 5. So now to name this, our parent chain is going to be cyclopentene, but we need to indicate which of the carbons within that ring have the double bonds. So in this case, it's cyclopenta 1,3-diene. And then because our double bonds start on carbon 1 and carbon 3, and then the ethyl group is on carbon 5, so it's going to be 5-ethyl cyclopenta 1,3-diene. This next molecule is almost the exact same as the previous one, except it doesn't have the ethyl group on carbon 5, so it's going to be named the exact same way as the previous, just without the 5-ethyl at the beginning. We still number with carbon 1 going through the double bond, so we're going to have cyclopenta 1,3-diene. In the next example, we have another benzene ring, but this time we have 3 substituents, so we need to determine which one has the highest priority, and in this case it's going to be the OH group. So we're going to use the OH as the parent chain, so it's going to be called phenol. And then if we number so that our remaining substituents have the lowest possible number, if we were to go clockwise, we would have 4 and 6, and if we go counterclockwise, we have 2 and 4, so that's the direction we want to go. So it's 2-chloro, 4-nitro, phenol. In the next example, we have a benzene that has a nitro group, a chloro group, and then another OCH3 group. So the anisole is going to be our parent chain, and the chlorine and nitro are each going to be substituents. Again, we want to number so that our remaining substituents have the lowest possible numbers, so I'm going to number the same direction as before with chlorine on carbon 2 and nitro on carbon 4. So altogether, this is going to be 2-chloro, 4-nitro anisole. And don't mind me just having struggles making this base line up. In the next molecule, we have an OH group, a chlorine group, and an amine group. So the OH is going to be the highest priority, so that's going to be carbon 1. And then from there, we want to number so that our substituents have the lowest possible number. So I'm going to go clockwise so that we have substituents on carbons 3 and 4 instead of going the other direction, which would put them on 4 and 5. Since OH is highest priority, our parent chain is going to be phenol, and then our substituents are 3-chloro, 4-amino. But in this case, A comes before C in the alphabet, so it's going to be 4-amino, 3-chloro, phenol. The next example has all the same substituents, just in a different order, but they're still going to have the same priorities. So the OH comes first, it's going to be carbon 1, and then to give the lowest numbers to the remaining substituents, sorry, my screen turned, we're going to number through the chlorine first and then the amine. So the parent name again is phenol, and then we have 4-amino, 2-chloro. So very similar to the previous one, but we have chlorine on 2 instead of 3. Finally, in this last example, it's another benzene ring with 3 substituents. In this case, we have an aldehyde, a chlorine, and an amine. That aldehyde is actually a mistake. Dr. Ciclini had wanted it to be a ketone, so I'm going to just draw in a methyl group. That way we can have our parent chain be acetophenone. We know it's the parent chain because it has a higher priority than both the chlorine and the amine. So if acetophenone is the parent chain, we're going to give that carbon 1, and then I'm going to number counterclockwise so that the remaining 2 substituents have the lowest possible numbers. So chlorine is carbon 2, amine is carbon 4, and since amine is higher in the alphabet, it's going to come first in the name. Question 4, we're asked to label the following molecules as either aromatic, anti-aromatic, or non-aromatic. So let's go ahead and start with this first one. Let's draw in the lone pairs on the oxygen. There are 3 double bonds and possibly 1 lone pair that would make up this conjugated system. In total, that would be 8 pi electrons, which we know is anti-aromatic, so those lone pairs are actually going to prefer to be sp3 hybridized so that it can avoid anti-aromaticity. So this molecule is going to be non-aromatic. So if a molecule is capable of avoiding anti-aromaticity by keeping its lone pairs in hybrid orbitals, it's going to do so. In the next example, the oxygen is replaced with an sp3 hybridized carbon. So this is not a complete ring of pi orbitals because that top carbon does not have a pi orbital. So this is non-aromatic. There's no other option. The next example is just the conjugate base of the previous example. So we have a lone pair here instead of the previous hydrogen. If this lone pair resonates into the ring, this would be fully conjugated. However, the total number of electrons would be 2, 4, 6, 8, which is anti-aromatic. As we know, anti-aromatic is unfavorable, so that lone pair is going to prefer to remain localized in a hybrid orbital, so this is no longer a fully conjugated system, and instead it is a non-aromatic. In this next example, that carbon has now been replaced with a nitrogen, which we know has a lone pair on it, and that lone pair is capable of resonating, but again, if it were to resonate, it would lead to anti-aromaticity. So that lone pair on the nitrogen is going to prefer to remain in a hybrid orbital to avoid aromaticity, so this molecule again is non-aromatic. Lastly, we have this 7-membered ring with a boron where the previous nitrogen had been. I'm going to draw in all of the pi orbitals, and boron is interesting because its formal charge is 0 when it only has 6 electrons, but it does still have an empty p orbital, so this is a fully conjugated system. Note that if we were to replace this boron with a carbocation, the carbocation would have a positive formal charge because there are only 6 electrons on this atom. However, if you look where boron is on the periodic table, you can see that boron has a formal charge of 0 when there are only 6 electrons. That means there are only 6 pi electrons total in this conjugated system, which meets the rules for aromaticity, and there's an empty p orbital on every atom within the ring, so this is an aromatic molecule. In the next example, we have a 5-membered ring with an oxygen and a nitrogen, each of them containing their respective number of lone pairs. There are 2 double bonds in the ring, which means that there are pi orbitals on these 4 atoms, and if the oxygen has a pi orbital, this would be fully conjugated. If that were the case, there would be 6 total electrons, because there's the 2 double bonds and the 1 lone pair. So this is going to be aromatic. In the next example, we have another 5-membered ring, but this time there are only 2 double bonds, and the nitrogen is not capable of completing this conjugated system because it already has 4 bonds, so it's sp3 hybridized. So this is going to be non-aromatic. The next molecule is another 5-membered ring, this time with a lone pair and 2 double bonds, so the total possible number of pi electrons is 6, which meets the rules for aromaticity. And if we were to draw in the pi orbitals, you would see that there is a pi orbital on every atom within this molecule, so this is aromatic. The next example is cyclobutadiene, so we have a fully conjugated pi system, and there's no way for those double bonds to avoid anti-aromaticity. So we have 4 pi electrons, so this is anti-aromatic. There's no way around it. There is a possibility that the molecule can slightly pucker to alleviate some of that high energy strain, but this is going to be aromatic. This next example is one that we already talked about, but I will go ahead and draw it again. So there's a lone pair here on that top carbon, so there are 4 total pi electrons. So if this were fully conjugated, it would be anti-aromatic. But to avoid anti-aromaticity, the lone pair is capable of residing in a hybridized orbital, which breaks the conjugated system. So this is going to be non-aromatic. In the last example, we have a 6-membered ring with alternating double bonds. The nitrogen does have a lone pair, but that lone pair is not participating in resonance because the nitrogen already has that double bond. So if we were to draw in all of the pi orbitals, there's 1 on either side of each of these double bonds, so this is a fully conjugated pi system, and there's a total of 6 pi electrons in the system, so these meet the rules for aromaticity. Okay, question 5. Which of the compounds below has an unusually acidic hydrogen on an sp3 carbon? So I think what makes the most sense to me is to find the sp3 hybridized carbon and draw in the invisible hydrogens. So here we have this carbon, that has 2 hydrogens. This one has 2 hydrogens. This one has 2 on either side, so it could be either of these that we're looking at, but they are equivalent. This one has none, and this one has 2. So the thing that's going to make these hydrogens more acidic is if the conjugate base is able to not just resonate, but specifically contribute to an aromatic system. So fully delocalized and follows the planar n4n+2 rule. So let's try drawing those out to see which one of these would make an aromatic ring. So this first one, if it were deprotonated, would have a lone pair here. And as we've discussed now 3 times in this video, this has a possible 4 pi electrons, which would be anti-aromatic. So this would not be super stable. If it's not aromatic, it is not going to be more acidic. We're trying to find something that creates an aromatic system. So this would be non or possibly anti, but we know that studies have shown that it's more likely that non than anti. This next one, cyclopentadiene, would look like this. I forgot to draw my negative charge. Don't forget that. This one has 2, 4, 6 possible pi electrons, and it has a completely delocalized ring of pi orbitals. So this meets the requirements for aromaticity. So this one would be aromatic. The next one, we could pick any of those 4 because they are all equivalent hydrogens. So I will just pick the top ones to keep with my convention. This one has the capability of resonating, but it does not have a completely delocalized ring of electrons, because if I were to draw in all of my pi orbitals, the carbon down here is sp3 hybridized and does not have a pi orbital. So this is not a candidate for aromaticity or anti-aromaticity. It does have a bit of resonance though, and that will make the hydrogen a little bit more acidic than your typical sp3 hybridized hydrogen, but not to the same extent as something that would create an aromatic system. So I'm going to say non-aromatic, but slightly acidic. Due to resonance. As we mentioned, carbon 4 doesn't have an sp3 hybridized carbon, so we can skip that one. And then the last one, forgive my 7-membered ring, I suck at these, as do most organic chemists. Hey, that one doesn't look so bad. Lone pair here, negative charge. If this one were to resonate, we would have 2, 4, 6, 8 pi electrons, which is anti-aromatic, so it would prefer to not resonate. It would prefer to remain in a hybrid orbital. So this would be non/anti, but specifically non. So that leaves us with answer 2 being our acidic hydrogen. This would have an unused release acidic hydrogen because it creates an aromatic ring. Finally, question 6, which of the following molecules below is most acidic? In other words, if we were to deprotonate one of these nitrogens and free up the lone pair to contribute to the ring, which of these rings would become aromatic? So let's again do the same thing as before and redraw the deprotonated form of these molecules. So this first one would look like this. This one is already aromatic. It doesn't matter that the nitrogen gained a lone pair because it already has a lone pair contributing to resonance. So this one doesn't significantly change. The lone pair is not involved in resonance, is how I'm going to say it. LP not involved in aromaticity. I said the wrong word. For this next one, when it comes to acidity, we're going to deprotonate from the positive charge first, typically. So, wrong color. This one would still have its hydrogen. This one would become a lone pair. And when we do that, we still have, so this one had a lone pair to begin with to create a full octet. It still has a lone pair. So this compound was already aromatic to begin with because it had 2, 4, 6 electrons. So gaining this new lone pair did not create an aromatic system because it was already aromatic, similar to number 1. So I'm just going to say the same thing for here. So both of these lone pair is not involved in aromaticity. For this next one, we have nitrogen here and here. Double bond, double bond, double bond. So this is already an aromatic compound, as evidenced by the fact that we have these 3 sets of double bonds. And again, if we were to draw in our pi orbitals, there's one on either side of every double bond, so this already is aromatic, which means that deprotonating the hydrogen gives us a new lone pair, but this lone pair, similar to this, is not contributing to resonance. So I'm going to say same, lone pair not involved in aromaticity. Next one, nitrogen. That looks bad. Double bonds here and here. If we lost one of our hydrogens, we would still have one hydrogen, but then we'd have a lone pair. Before, this compound was sp3 hybridized. Now it has the possibility of resonating in this lone pair, making it sp2 hybridized with a p orbital. So this created an aromatic compound that did not previously exist. So this lone pair contributes to aromaticity. So this is likely our answer, but we can finish off with the final molecule just to confirm. We have this nitrogen, double bond, double bond, double bond. If we lose the hydrogen, that means we'd have a new lone pair. But that doesn't make a difference because this molecule is already aromatic because we already have 6 electrons and we already have a fully conjugated system. So the lone pair generated does not contribute to aromaticity. So final answer, is number 4. And that brings us to the end of this recitation packet. As always, if you have any questions or would like clarification about anything in this video, please feel free to send me an email and I will get back to you on that.